big question. You really need to be thinking about this in order to be able to solve it. What is this? This is a space which I can call Rx10, and I can define this Rx10 as, well, all degree 10 polynomials. Let me write a degree 10 polynomial. It looks like this: a0 plus a1x plus dot dot dot. I hope you didn't think I was going to write all 11 terms. That would be silly, right? Such that all the coefficients ai are real, and I add a condition which I think most people usually forget, and that is we need the coefficient of the biggest term, the biggest x to the 10, to not be equal to 0. This is very important. I might even say that this is key to solving the problem. Because if this is 0, then you will get at most a degree 9 polynomial or a degree 8. You see where this is going. Like if this is 0, then you don't have a degree 10 polynomial anymore, and you exit your vector space. Now, luckily, okay. Yes, luckily, I have a checklist to find out if this is a vector space or not. So this is good. I'm happy. Let me also tell you this beforehand. So addition and multiplication are defined in the usual way. And the usual way means what does it mean? So normal addition, normal multiplication by scalar, no caveats whatsoever. And as we know them, these operations are completely commutative and associative. So this is good. Usually this is number 0 because nobody actually checks it, because usually it is obvious. Now we'd like to see if V is closed under addition and scalar multiplication. V is closed under addition if I can add two vectors which are in my vector space to get something that's in the vector space. So let's start by doing that. Let me choose. So right now I'm asking the question, is this the case? Just to make it clear, I'm asking the question. Well, this is asking the question to now start to try to solve it. I choose an arbitrary vector in my vector space. Now this is a vector space of polynomials, so my vector should probably look something like this. I mean, this is of course if I choose the standard basis of 1x, x squared, so on. But let's just skip the technicalities. V2 would be, let's say I'll call it B0, B1, dot 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 B10. So something that's different. And the conditions on the coefficients apply. And let's say I add V1 plus V2 and see what I get for myself. A0 plus B0, A1 plus B1, and so on and so forth. A10 plus B10. So I hope this is good. I'll shrink this for now. So just to make a little bit more space. And now I have a new vector. Let me define, just for the sake of comparison that we're going to do now. I'll define, I don't know, a tilde of 0 to be a0 plus b0. I'll do this for all indices, so I'll choose ai to be, ai tilde to be ai plus bi. Maybe I'll just choose ci, because why use the same a again? That doesn't make sense. And here's why I do this specifically. I do it because I want to check these two things. Is this true and is that true? You can try to pause the video and think about this. I can tell you something for sure. That is, if A0 is in R and B0 is in R, I mean AI in general, then probably CI is going to be in R. So CI is going to actually be in R. This is actually going to be true, because simply if I choose a BI, which is a real number, and I add a real number to a real number, I will always get a real number. The field of reals, it's a field that's closed. But regardless of this piece of info, adding two real numbers gives you a real number, for sure. So this is fine. But what about the other one? C10, which is equal to A10 plus B10 is not equal to 0. We're asking the question. We don't know this yet. So we've gone from this question to that question now. And this might not be clear. Let's see what we have in mind. What we have, well, not in our mind, but in our hands, is that A10 is not equal to 0 and B10 is not equal to 0. So this looks promising, A10 is not equal to 0, B10 is not equal to 0. Then if I add two non-zero numbers, I should get a non-zero number, right? Wrong. Just absolutely, completely wrong. I don't know what you were thinking of. Just choose any two additive inverses. Just choose 1 and minus 1. These are non-zero numbers, which have a sum of 0. So the fact that these two are not equal to 0 does not imply that C10 is equal to 0. Well, not equal to 0, which means that this is not going to be a vector space. Let me try to formulate this idea more concretely. So I do this, of course, by means of the example that I just mentioned. 1 plus minus 1 is equal to 0. Remember, I'm talking in terms of A10 and B10. So let's take two vectors in the vector space, which give me a vector that is not in the vector space. With this info, you should be very close to finding such an example. I will give it now. Simply choose a polynomial, just x to the 10, and choose another polynomial, which will be minus x to the 10. Then these two vectors, despite being both in the vector space of, real numbers of degree 10, they will add up to 0, which is not in the vector space. So x10 is in the vector space. The other x10 is in the vector space, but 0 is not in the vector space, because 0 is a degree 0 polynomial. It's not a degree 10 polynomial. So this is just one example, but there's an infinite class of such examples. And this class is precisely when you choose A10 to be the additive inverse of B10 for any polynomial. And you add them together. When you do that, you get the 0. But this is on a very basic level. And now we don't have that this is a vector space. By a very basic level, I mean that you could also make this more complicated by looking at scalings and addition together and seeing if it fails. But in principle, if scalar multiplication or addition fail, then the more complicated operation of combining these two operations should also fail. So it is actually sufficient, more than sufficient, to look at these ones. But perhaps what I was trying to say is that really for any polynomial, if you choose any two polynomials, there's always a constant which I can scale the first polynomial by to cancel out the other constant, which is the coefficient of x to the 10. So I can violate this A10 condition in every single way you could think of. So for example, if I take 97x to the 10, I can always find a polynomial which it will be minus 1 over 97 x to the 10 plus ... And this will be 97x to the 10 plus ... This will always not be in my vector space. And this is what I'm talking about when I say that you can violate this in any way possible. So there is a huge gap in this vector space which might not be amendable unless you can inflict huge changes to this vector space. For example, if you allow this to be a vector space, if you allow this to be the set of all the degree 10 polynomials or less, and you go all the way down to 0, then it will be actually the case that you'll have a vector space, because you don't need to worry about the degrees of the polynomials. If you add a polynomial, you get another polynomial. You subtract a polynomial, you get another polynomial. And the maximum degree that a polynomial can attain is 10. You can't reach a higher degree for a polynomial. The only way you would do that is by vector multiplication, which is not defined. We only define addition and scalar multiplication. So I'm just giving you more and more and more ideas. The problem was already done when we wrote this big no, but I'm giving you ways to maneuver and ideas to ponder. I hope this was of great help.